As previously, for every increase in voltage, we observe a proportionate increase in current and a geometric increase in power. In short, Ohm's law is linear, whereas power is geometric. The difference between current as a function of voltage for the 560 ohm resistor and the 750 ohm resistor being the rate of change or slope, which is an understandable reflection of the differing resistance values. For each operating condition, the smaller 560 ohm resistor experiences more current and dissipates more power, whereas the larger 750 ohm resistor experiences less current and dissipates less power. As a result, the slope of current and power as a function of voltage for the smaller 560 ohm resistor appears steeper, and the larger 750 ohm resistor less so. These plots are graphical evidence of our understanding of Ohm's law and power. First, given constant resistance, less voltage yields less current and less power. Conversely, more voltage yields more current and more power. Second, given constant voltage and more resistance yields less current and less power. Conversely, given constant voltage, less resistance yields more current and more power. The nature of these plots and the conclusion drawn from them should be understandable, and if not, I'm asking that you pause the lecture and stare at them without blinking until you do understand them on every level that I'm asking you to do so. Copy these theoretical calculations down in your notes for the basis of comparison. Let's see if we can use real-world instrumentation to verify these theoretical results. I'll walk you through a couple of the first observations step by step. The 4-band resistor color code for a nominal 560 ohm resistor is green, blue, brown, gold, meaning 5, 6, followed by 1, 0. Given a plus or minus 5% tolerance, we might expect this resistor to be between a low of 532 ohms and a high of 588 ohms. An ohm meter measuring the resistance of a resistor matching this description demonstrates it has a resistance of 556.7 ohms, well inside the expected tolerance range. This being said, given this resistor has a slightly smaller resistance than its nominal value, we might understandably expect our observed current to be slightly higher than our theoretical calculations might suggest. First, let's use a DC voltmeter to establish a 2-volt differential. This is the unloaded voltage, meaning it is the voltage established by the supply when it is not providing current to a circuit. We need to build the circuit and recheck voltage in the loaded condition to make sure it hasn't changed. Turn off the power supply. Again, let's current limit this source to 1/4 of 500 milliamperes or 125 milliamperes by turning the adjustable current limit knob 1/4 turn clockwise. This current limits the source to 125 milliamperes or below in the event we make a mistake. Install the nominal 560 ohm resistor on the protoboard such that one terminal is landed at node 5A through E, and the other terminal is landed at node 5F through J across the ditch. Build a complete circuit by landing the positive terminal of the source at node 5A through E and the negative terminal of the source at node 5F through J. The one and only path from node 5A through E to 5F through J across the ditch is through the nominal 560 ohm resistor. To check the loaded voltage, land the red lead of the voltmeter at node 5A through E and the black lead of the voltmeter at node 5F through J. Turn on the power supply. The DC voltmeter demonstrates the adjustable source hasn't deviated all that much from the unloaded state when in the loaded condition and actually supplying current to an element. Power off the power supply. Let's now use a DC ammeter to measure current through this system. Consider the original unmodified circuit. We need to break the circuit and insert the ammeter such that all current passes through the ammeter. Break the circuit so that the source positive terminal is no longer landed at node 5A through E, but rather dangling out in space. This is an open circuit and no path exists through the resistor. Now insert the ammeter to bridge the open such that all current must pass through it. Out of the power supply positive terminal, into the ammeter indoor, through the ammeter, out of the ammeter outdoor, into the nominal 560 ohm resistor at node 5A through E, through the resistor, out of the resistor at node 5F through J, and into the power supply negative terminal. A complete circuit has been established and all current must pass through the ammeter. When we power on the power supply, the ammeter displays current through this circuit, and thus power dissipated by it is consistent with our theoretical calculations. We now need to repeat these observations in 2-volt increments up to 12 volts. I'm going to save you the trouble and do it myself. Here's what I observe in the following conditions. At 4 volts, we observe 7.1 milliamperes of current. At 6 volts, we observe roughly 10.7 milliamperes of current. At 8 volts, we observe 14.4 milliamperes of current. At 10 volts, we observe 17.9 milliamperes of current. And finally, at 12 volts, we observe 21.4 milliamperes of current. Let's do the same experiment for the 750 ohm resistor. The 4-band resistor color code for a nominal 750 ohm resistor is purple, green, brown, gold, meaning 7-5 followed by 1-0. Given a plus or minus 5% tolerance, we might expect this resistor to be between a low of 712.5 ohms and a high of 787.5 ohms. An ohm meter measuring the resistance of a resistor matching this description demonstrates that it has a resistance of 760.9 ohms, well inside the expected tolerance range. This being said, given this resistor has a slightly higher resistance than its nominal value, we might understandably expect our observed current to be slightly lower than our theoretical calculations might suggest. At 2 volts, we observe 2.7-ish milliamperes of current. At 4 volts, we observe 5.3 milliamperes of current. At 6 volts, we observe roughly 8 milliamperes of current. At 8 volts, we observe 10.7 milliamperes of current. At 10 volts, we observe 13.3 milliamperes of current. And finally, at 12 volts, we observe approximately 16 milliamperes of current. If you were to compare the actual observations with our theoretical calculations from before, there's an almost 1-to-1 match for each resistor. Any minor variations observed might be the results of resistance variation, instrument calibration, or even human interpretation. These minor variations aside, the electrical properties we've thus far discussed do indeed seem to be true and verifiable by experimental observation to a reasonable degree of accuracy. Put your hand on top of the internet and repeat after me. I believe. If only all labs could go so smoothly. In this spirit, I present to you a handful of simple troubleshooting scenarios you might run across in a lab environment. Put your understanding of instrumentation and circuit construction to the test with these series of example problems and see if you can figure out what's wrong and then recommend a course of action to correct the problem. Our first scenario features a nominal 560 ohm resistor at 6 volts. Ordinarily, we expect to observe 10.7 milliamperes of current through it. However, when we insert an ammeter into this circuit, it registers no current. Additionally, a voltmeter registers no voltage differential across the resistor. Here's a close-up picture of the circuit including the ammeter. Here's another close-up picture of the circuit including the voltmeter. Here's yet another close-up picture of this circuit without any instrumentation at all. No current through, no voltage drop across. What's the problem? By all means, pause the lecture and try this on your own. If you're tracking, you should have come to the following conclusion. One of the first questions you should ask yourself when you observe no current and no voltage drop is whether you've turned the power supply on or not. You'll be surprised how often this problem is fixed by pushing the button labeled on. In this scenario, however, the source is clearly on. However, we're still not observing any current. No current is a clear sign that there is an open somewhere in this circuit. You know, the circuit has the positive terminal of the source landed at node 5A through E. One terminal of the nominal 560 ohm resistor also landed at node 5A through E. The other terminal resistor landed at node 5F through J across the ditch. However, the negative terminal of the source is landed at node 3F through J. No connection exists between node 5F through J and node 3F through J above it, and no path for current exists. This is an open and no current will flow through this circuit, nor will any voltage be dropped across the resistor. Close visual inspection of the circuit has identified the problem. Here's a much better implementation of this circuit where the positive terminal of the source and one terminal of the nominal 560 ohm resistor are both landed at node 5A through E, and the other terminal of the resistor and the negative terminal of the source are both landed at node 5F through J across the ditch. A complete circuit has been established and one and only one path from node 5A through E to node F through J exists such that all current will pass through the nominal 560 ohm resistor. Here's another troubleshooting scenario using the same circuit. A 560 ohm resistor at 6 volts, ordinarily expected to draw 10.7 milliamperes of current. Let's say you made the grave error of leaving your lazy lab partner unsupervised for a moment. In your absence, they've built a circuit, and to your horror, they flip on the power supply and the overload LED illuminates. Here's what you observe when you inspect their circuit. By all means, pause the lecture and troubleshoot this circuit. What's wrong? If you're tracking, you should have come to the following conclusion. This is indeed a 6-volt source, and this is in fact a 560 ohm resistor. However, they've built the circuit on the protoboard incorrectly. Note, both terminals of the resistor are landed at the same node 5A through E. Additionally, both the positive and negative terminals of the source are also landed at the same node 5A through E. Recall that all points in node 5A through E are connected via the conductive clip inside the insulating plastic block. A resistor installed in this fashion presents no opposition to the source, and by landing both the positive and negative terminals of the source on the same node, we've in effect directly tied the source positive and negative terminals together with no current controlling element between. No wonder the source enters an overload condition. Here we've current limited the DC power supply to 125 milliamperes, and the illuminated overload LED indicates it's pegging this user adjustable limit. Turn off the power supply. Grab a thin but very stiff bamboo cane and strike your lab partner viciously across the shins and remind them never to touch anything in your absence. Again, a visual inspection of the as-built circuit has identified the problem. As previously, here's a much better implementation of this circuit where the positive terminal of the source and one terminal of the resistor are both landed at node 5A through E, and the other terminal of the resistor and the negative terminal of the source are both landed at node 5F through J across the ditch. A complete circuit has been established, and one and only one path from node 5A through E to node 5F through J exists such that all current will pass through the nominal 560 ohm resistor. The resistor must be in the circuit to keep current under control. Here's one more troubleshooting example. Let's say you take pity on your lazy lab partner and offer to run them through a couple practical exercises to get them back on track. Since ammeters seem to be the most difficult task for first-timers, you ask them to set up an ammeter to measure current through this circuit. Again, a 6-volt source with a 560 ohm resistor, ordinarily expected to draw 10.7 milliamperes of current. Let's say they build the circuit, set up the ammeter, and then install the ammeter in the following fashion. Take a look at this and tell me if they've installed the ammeter correctly, and see if you can predict what might happen if they turn the power supply on. By all means, pause the lecture and try this on your own. What's wrong? If you're tracking, you should have come to the following conclusion. This is not how you install an ammeter. You recall that ammeters must be placed in series or in line with elements of interest such that all current passes through the ammeter. Placement of an ammeter in parallel with an element of interest can have disastrous consequences. Recall that ideal ammeters are modeled as 0 ohm resistances through which substantial current can flow. Additionally, recall that the resistance of a parallel configuration of elements is always smaller than the smallest resistor constituting the parallel relationship, and that 0 ohm shorts inside parallel configurations effectively short out the entire parallel configuration. An ammeter configured in this fashion will present no opposition to the source, and substantially, theoretically infinite amounts of current can flow. This could damage the meter, your circuit, or yourself. Never, ever put an ammeter in parallel. Here the DC power supply is current limited to a maximum of 125 milliamperes. When we turn on the power supply, an ammeter incorrectly configured in this fashion demonstrates roughly 125 milliamperes, our permitted maximum, flows through the ammeter. The source indicates it's in an overload condition by illuminating the overload LED. Again, we've current limited this source to 125 milliamperes. If this source was capable of producing, let's say, 100 amps, all 100 amps would be diverted through the ammeter installed in such a fashion. This is a surefire way to destroy the device and those in close proximity. Here is a much better way of inserting an ammeter in a circuit. Consider the original unmodified circuit. Power off the power supply. Break the circuit such that the source positive terminal is no longer landed at node 5A through E, but rather dangling out in space. This is an open circuit and no path exists through the resistor. Now insert the ammeter to bridge the open such that all current will pass through it. Out of the power supply positive terminal, into the ammeter indoor, through the ammeter, out of the ammeter outdoor, into the resistor, through the resistor, out of the resistor, and into the power supply negative terminal. A complete circuit has been established and all current will pass through the ammeter. When we power on the power supply, the properly configured ammeter displays an amount of current consistent with our theoretical calculations. Alright, one last troubleshooting example before I cut you loose. Consider a nominal 150 ohm resistor rated for low power applications of less than a quarter watt or 250 milliwatts. See if you can calculate the current through the 150 ohm resistor and the power dissipated by it when it's being driven by a 20 volt source. By all means, pause the lecture and try these calculations on your own. If you're tracking, you should be able to predict what's about to happen. When we turn on the power supply, the resistor quickly begins to smoke, the paint turns an ugly shade of brown, then black. If I left it here long enough, it would probably catch fire and melt. My question to you is this: did you do the calculations like I asked? If not, you just died. Do the calculations first. Don't walk into a gunfight with a dull knife. Know what to expect. Don't be surprised when stuff blows up in your face because you're too lazy to do the calculations. At the very least, calculations in advance of observations allow some basis of comparison to let you know if your observations are inside the range of theoretical expectations or if they're wildly off the mark, indicative of some other problem. If you did like I asked, you'll realize a 150 ohm resistor driven by a 20 volt source would draw roughly 133.3 milliamperes of current and dissipate approximately 2.7 watts of power, well above the specified quarter watt or 250 milliwatt power rating for this particular resistor. No wonder it went up in flames. The point being, snap out of it. Do the calculations first. Know what to expect. Electricity is as dangerous as it is useful, and my intention is that you understand, appreciate, and respect electricity, not fear it. The only way you can do that is get involved, pay attention, and do the calculations first. All right, that about wraps it up for this quick verification of Ohm's law. In conclusion, this lecture demonstrated and verified DC Ohm's law using real-world components and instrumentation. Additionally, we took a quick look at a couple troubleshooting scenarios. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.